Hello, it's Stat 134, Lecture 29. Last time we covered the beta distribution, section 4.6. The beta distribution has two parameters, R and S, and the density is given below with the variable part highlighted. The beta distribution parameter is between 0 and 1. An application of the beta is as a generalization of the uniform ordered statistic. So in other words, if you throw n darts at 0, 1, the kth order statistic is a beta kn minus k plus 1. Letting n be 1 and k be 1, we see that the standard uniform is a beta 1, 1. The beta RS represents a distribution of probabilities. It's useful in Bayesian statistics to be a distribution for probability. And from lecture 2, we saw that the posterior is proportional to the likelihood times the prior. And if we let the prior be a beta, so that would have a variable part p to the r minus 1, 1 minus p to the s minus 1, and the likelihood be either binomial or a geometric, with the variable part also in purple, then you can see that when you multiply the likelihood and the prior, that you'll also get a beta, because the variable part of that product will still be a power of p times a power of 1 minus p. So the prior being beta means that the posterior will be beta, and the posterior is an update of the distribution of p given your data. Now, if you get new data coming in, you could let that posterior be your new prior and get a new posterior, which will also be beta. And so you can cycle like this. As you get more and more data, you get an updated beta distribution for p. Today we're going to do competing exponentials and marginal density expectation. Hence, we're going to finish section 5.2. So section 5.2 on competing exponentials, we covered this last time, but I want to give a few more examples. So if x and y are independent lifetimes of two bulbs, we were asked to find the probability that y is greater than x. So we are integrating the joint over the region highlighted, shaded in the picture below, and we get lambda over lambda plus mu, which makes sense because lambda is the rate. So if mu is very small, mu is the rate that light bulb Y burns out, then, so if mu is very small, then the probability that Y is greater than X would be close to 1. If mu is very large, then the probability that Y is greater than X will be close to 0. That makes sense because if mu is large, that means that the rate of if mu is large, that means that the rate of burning out is quite large, so the chance that Y will outlast X is very small. So as an application of this, we saw that if you're first in line to have your question answered by Brian and Yiming, who are busy with current students, your question will be answered as soon as the first UGSI finishes. The time spent with with student by Brian and Yiming are independent exponentially distributed with positive rates lambda b, lambda y. Brian's distribution is exponential lambda b, Yiming's is exponential lambda y. So to find the probability that Yiming will be the one answering your question means that we're looking for the probability that y is less than b, or probability that b is greater than y, which, since b and y are competing exponentials, that will be lambda y over lambda y plus lambda b. What's the distribution of your wait time? Well, the wait time is the minimum of y and b. And a good strategy to find the distribution of the minimum is to look at the probability that w is greater than w, because for the minimum to be greater than w means that y is greater than w and b is greater than w, and we know that y and b are exponentially distributed. So I've just written down the survival function for y and b, and so I see that the survival function for w has constant lambda y plus lambda b and is exponential. So that is how you would do that. Moving on to marginal densities, let's recall the discrete case. So the marginal probability of x, what we do is we can get it from this table by, for a fixed x here takes value 0, 1. So if we say x is 0, the probability that x is 0 is the sum of the joints with x is 0. So we sum through all the y values. Similarly, the marginal probability for y, we sum through the x values of the joint. So the analog in the continuous cases, we just replace our sum by an integral and the joint probability mass function with the joint density function. So here's an example. So the marginal density is this joint. We've seen this. X here is the first order statistic, y is the sixth order statistic. And so the integral, the double integral over all the values of x and y, of course, is 1. But because the support of this joint density is just in the triangle on the picture on the right here, we can say that the integral for x between 0 and 1 and y from x to 1, that integral of the joint is 1. And so furthermore, the marginal density is this inside integral. So it is the integral from y is x to y is 1 of 30y minus x to the 4th power, which you can solve by u substitution, and you get 6 times 1 minus x to the 5th power for x between 0 and 1. Similarly, we can do this for y, and we get 6y to the 5th. Here we are integrating out x, and you can see that x and y aren't independent because the joint is not the product of the marginals. For expectation, it's just the definition that you would expect. We can check our definition by looking at the special case where g of x, y is just y, and using our definition, bringing y outside the inside integral, and recognizing the inside integral is just the definition of the marginal density of y. we can see that the expectation is 6 over 7, which makes sense because y is the 6th order statistic, which is a beta 6,1, and we know what the expectation of beta, we know that the expectation of a beta 6,1 should be 6 over 6 plus 1, or 7, so that makes sense. So then I asked you guys to practice this problem. So S and T are IID exponential lambda. X is the max of S and T. Y is, X is the min and Y is the max. And I asked you to find the joint density of X and Y. So this problem is very similar to how we found the joint density when S and T were uniform, standard uniform. So we have the density of S or T drawn here. S or T takes values greater than 0. And so we're going to look at the probability that X is in dx and Y is in dy to find the density. So the probability that X is in dx and Y is in dy is, by the multiplication rule, it's the probability that X is in dx times the probability that Y is in dy given that X is in dx. So the probability that X is in dx would be 2 choose 1 lambda e to the minus lambda x, because, well, to throw one dart and have it land in dx, the chance of that is just the area of the rectangle, which is lambda e to the minus lambda x. And we have 2 darts, so that's twice the probability. So hence the 2 choose 1. Now, given that a dart has landed in dx, there's 1 dart left, and its chance of landing in dy is lambda e to the minus lambda y dy. And so we can pick out the joint density here. So then I asked you to find the marginal densities as a concept test question. And so I can think of two ways to do this, but I'll be curious to see what you say. So one method is just using the definition of the marginal. Here I'm integrating through all the values of y. Now because y is greater than x, because y is the max, we integrate from x to infinity the joint, and we get 2 lambda e to the minus 2 lambda x. Or you could use our sort of our CDF method, let's call it, because x is the min. We'll look at the probability that x is greater than x, which is a probability that s is greater than x and t is greater than x, which is a probability that s is greater than x squared. And the probability that s is greater than x, that's just a survival function of s, which we know. And so we get the CDF is 1 minus e to the minus 2 lambda x. You take the derivative of that and you get your density. To do the second question, we'll do it the same way. For method 1, we're just integrating out x, and x is smaller than y. So we're integrating x from 0 to y, and we'll get the answer boxed there, which is B. Or you could use the CDF method, and because it's a max, we'll find the probability that y is less than y is probably that s is less than y squared, and that's 1 minus e to the minus lambda y quantity squared. Take the derivative of that and you get answer B again. And just a fun check that x and y are independent, you can check that the joint is not the product of the marginals. Okay, have a great day. I'll see you next time.